Welcome all. In this lecture, we are going to solve example number 8. Plot the root locus pattern for a unity feedback system whose forward part transfer function is given as g of s equals to k into s plus 1 over s plus 2 s square plus 2s plus 5. So here in this question we are given with a open loop transfer function and we need to find and plot the root locus diagram. So we will follow all the 9 steps to plot the root locus on the S-plane. Moving to the step number 1, that is determination of number of poles. And number of zeros. So firstly we will calculate the number of zeros. We all know that on equating the numerator part to 0 we will get all our zeros. So on equating the numerator part, that is s plus 1 equals to 0, we will get our first 0 which lies at s equals to minus 1. So 0 z1 lies at s equals to minus 1. And since there are no remaining terms in the numerator, that's why number of 0 is equals to 1 only. Moving on to the next step, that is calculation of number of poles. So number of poles can easily be determined by equating the denominator part of an open loop transfer function equals to 0. So on equating s equals to 0, we get our first pole which lies at s equals to 0. On equating s plus 2 equals to 0, we get our another pole which lies at s equals to minus 2. On solving this quadratic equation, we will get another 2 poles. So let's solve it. By the help of a formula, s equals to minus b plus minus under the root b square minus 4ac divided by 2a. So s will be equals to, here b value is 2, so minus 2 plus minus under the root 2 square minus 4, a value is 1 here and c value is 5 here, divided by 2 into 1. So s value will be directly equals to minus 2 plus minus under the root 4 minus 20 over 2. So s will be equals to minus 1 plus minus 2 iota. So our pole P3 will lie at minus 1 plus 2 iota, and pole P4 which will also lie at minus 1 minus 2 iota. So the number of poles is equals to 1, 2, 3 and 4. So in this question we are going to deal with 4 poles and 1 zero. Moving on to the next step, that is calculation of number of branches of root locus. So number of branches of root locus can easily be determined by the formula maximum of number of poles comma number of zeros. So maximum of, since number of pole is equals to 4 and number of 0 is equals to 1, that's why we can say that number of branches of root locus is exactly equals to 4. Moving on to the step number 3. That is calculation of number of asymptotes. Since the number of asymptotes is equals to number of poles minus number of zeros, thus since number of pole is equals to 4 minus number of 0 is equals to 1 only, that's why we can say that number of asymptote is equals to 3. Moving on to next step, step 4, in which we will calculate the centroid of asymptotes. So the centroid of asymptotes can easily be calculated by the formula x equals to summation of real part of S, real part of poles, minus summation of real part of zeros, whole divided by number of poles minus number of zeros. So x will be equals to, since we have 4 poles, pole P1 lies at 0, pole P2 lies at minus 2, pole P3 lies at minus 1 plus 2 iota, pole P4 lies at minus 1 minus 2 iota, and we have 1 0 that lies at minus 1. So on summing the real part of all the poles, that is, this is the real part, this is real part, here minus 1 is the real part, minus 1 is the real part. So on summing 0 plus minus 2 plus minus 1 plus minus 1, 0 plus minus 2 plus minus 1 plus minus 1 minus real part of zeros, that is minus 1, whole divided by number of pole, that is 4. So on solving we get minus 4 plus 1 divided by 3. So we get x equals to minus 1.33. This is our centroid of asymptotes. Moving on to the step number 5, that is calculation of angle of asymptotes. Since angle of asymptotes can easily be determined by the formula phi equals to 180 multiplied by 2m plus 1 divided by number of poles minus number of zeros. Thus, for the calculation of asymptotes, we have to first determine the value of m. And here we all know that the value of m starts from 0 and end at number of pole minus number of 0 minus 1. So it will start from 0 and end at, since number of pole is equals to 4, number of 0 is equals to 1 minus 1. So the value of m will be equals to 0, 1 and 2. So for each value of m, we have to calculate the angle of asymptotes. Let's calculate the angle of asymptotes. At m equals to 0, you get phi1 equals to 180, 2 multiplied by 0 plus 1 divided by number of pole is equals to 4 minus number of 0 is equals to 1 only. So later on solving, we get 60 degree. At m equals to 1, we get phi 2 equals to 180 into 2, m value is 1, plus 1 divided by number of pole 4 minus number of 0, that is 1. So later on solving, we get 180 degree. At m equals to 2, we get phi 3 equals to 180 to m value is 2 now, plus 1 divided by 4 minus 1, that is 300 degree. So these are the three angle of asymptotes: 60 degree, 180 degree and 300 degree. Moving on to the next step, that is step number 6. Root locus lies on which part of real axis? So for this, we have to first write all the poles and zeros. So pole P1 lies at 0, pole P2 lies at minus 2, pole P3 lies at minus 1 plus 2 iota, pole P4 lies at minus 1 minus 2 iota, and we have one 0 that lies at minus 1. For this we have to plot the S-plane. This is the imaginary axis, this is the real axis. On P equals to 0, here is pole P1. On S equals to minus 2, here is pole P2. On S equals to minus 1 plus 2 iota, here is 2, here is minus 2, here is minus 1. So minus 1 plus 2 iota will be here, and pole P4, that is minus 1 minus 2 iota, will be somewhere here at this point. So this is the successful plotting of all the poles, and we have also one 0 that is at minus 1. So this is 1 0. Now we have how many number of regions? This is the first region, that is denoted by x1, which lies from 0 to plus infinite. Region x2 is here, that ranges from minus 1 to 0. Region x3, that ranges between minus 2 to minus 1. And region x4, which lies between minus infinite to minus 2. Now let us calculate that how many poles or zeros lies in the right hand side of region x1. So by the observation we can easily say that there are no poles or zeros that lies in the right hand side of x1. So it is an invalid region. Talking about the region x2. Now check how many poles or zeros lies in the right hand side of x2. Since only one pole at s equals to 0 lies in the right hand side of x2. Talking about x3, only one zero and one pole lies in the right hand side of x3. This is one zero and this is one pole that lies in the right hand side of x3. So total two things that lies in the right hand side of x3. Talking about x4, now calculate how many poles or zeros lies in the right hand side of x4. So one pole, one zero and one pole, that is two poles and one zero, total 3. Since 1 is an odd number, that's why it is a valid region. Since 2 is an even number, that's why it is an invalid region. Since 3 is an odd number, that's why it is a valid region. So we can easily say that x2 is a part of the real axis onto which the root locus lie, and also root locus lies from minus infinite to minus 2. So root locus lies from minus 1 to 0 and root locus also lies from minus infinite to minus 2. Since in this figure we can say that by the observation there are no conjugate poles that lies on the real axis or no conjugate zeros that lies in the real axis. That's why the concept of break-in and breakaway point does not exist. Break-in or away point not exist. But there are two imaginary poles. So in case when in the question we have the imaginary poles, then in that case the angle of departure will always be exist. So we can say that angle of departure will exist. So in the next step we will calculate the angle of departure. So let's calculate the angle of departure. It is our S-plane, it is our imaginary axis, it is our real axis. Firstly we will plot all the poles and zeros onto the S-plane. So pole P1 lies at 0, pole P2 lies at minus 2, here is 2, here is minus 2, here is minus 1, so in another pole that is minus 1 plus 2 iota that lies here, and pole P4 lies here, that is minus 1 minus 2 iota, and at s equals to minus 1 we have 1 0. Now let's take this pole as a reference pole. So taking this pole as a reference pole, we will meet all the poles to this pole by pointing a line from all the pole towards this pole. So making a line which will point towards the reference pole. Here also we will make a line and it will also point towards reference pole. From this 0 we also make a line and point at reference pole, and from this pole we also draw one more line that will go on the top towards the reference pole. Now firstly we will calculate the angle between this reference pole and this pole. So this angle we will calculate. So the angle theta P1 will be equals to tan inverse of y over x. Here the y value is 2 and x value is 1. So tan inverse of 2, so we get 63.43. Calculating another angle that will arise from the pole, this pole to this reference pole. So theta P2 is equals to this angle we will going to calculate. So this angle will be exactly equals to, here is the 90-degree angle, so we will simply put 90 plus, and this angle will easily be equals to tan inverse of y over x. Here the y value is 1 and x value is 2. That's why 90 plus 26.56 we get. So it will be exactly equals to 116.56. Moving on to the next angle, that is this angle. So theta P3 will be equals to 90 degree only, because it is a right angle. So this is all about all the three angles which are made by poles to this reference pole. Now calculating theta z, that is the angle made by this 0 towards this pole, that is this angle. By observation we can easily say that it is a right angle. That's why theta z is equals to 90 degree. And we all know that theta d, that is angle of departure, is equals to 180 minus theta p minus theta d, theta z. Here theta p is equals to sum of all the angles of the pole, and theta z is equals to sum of all the angles made by the 0. So 180 minus, calculating the sum of all the pole angle, that is 63.43 plus 116.56 plus 90 degree minus theta z, that is 90 degree. So we get 180 degree minus 180 degree, that is 0. So angle of departure is equals to 0 only.